Hello everyone, today we are going to discuss different aspects of first order reaction. This is a very important topic. From this topic, questions are asked almost every year in board and different competitive examinations like medical, engineering, NET, GATE, etc. This lecture would be helpful for you guys in building up basic concept regarding first order reaction. Once you have basic concept, you would be able to solve different problems based on it. So first order reaction is basically a reaction in which the rate of reaction is directly proportional to the first power of the concentration of the reacting species. The examples of the first order reactions are radioactive decay, decomposition of dinitrogen pentoxide into NO2 and O2. Hydrogenation of ethylene to get ethane. So these are the three examples that I have mentioned as an example of first order reaction. Now we will discuss rate equation for the first order reaction. Suppose we have a reactant species A and it forms product. So the rate law for first order reaction can be written like as rate is equal to minus dA upon dt is equal to k a to the power 1, or simply we can write minus dA upon dt is equal to K concentration A. This is equation number 1, and this equation number 1 is called differential form of rate law of first order reaction. After rearranging equation number 1, we will get dA upon A is equal to minus K into dt. Where K is rate constant or sometimes called a specific rate. dA upon A can be written d ln A. That will be equal to minus K into dt. This is equation number 2. So if we integrate equation number 2, we will get ln A is equal to minus kt plus C, where C is a constant called integration constant. So now we will find out the value of C by putting limiting conditions. So limiting conditions are, if time is equal to 0, at time is equal to 0, A will be equal to A0, means initial concentration. So putting the value of A at time t0 in equation number 3, we will get ln A0 will be equal to minus k into 0 plus C, or simply we can say that the value of C is equal to ln A0. If we put the value of C in equation number 3, we will get ln A is equal to minus kt plus ln A 0. So rearranging this equation, we can get kt is equal to ln A0 upon A. So this is equation number 4, and the equation number 4 is called integrated form of rate equation for first order reaction. Now we are going to discuss half-life of first order reaction. Half-life of first order reaction. Half-life of first order reaction. We have seen just now that the integrated form of rate law equation for first order reaction is Kt is equal to ln A0 upon A. At T is equal to T half, where T half is half-life, A will be equal to A0 upon 2. So putting the value of A into this equation, we will get K into T half is equal to ln 2. Or we can write K into T half is equal to 2.303 log 2, or K into T half will be equal to 2.303 into 0.301, or we can write Kt is equal to 0.693, or we can write T half is equal to 0.693 upon K. So if you see the T half equation for the first order reaction, there is no concentration term. So the half-life of first order reaction is independent of the initial concentration of the reactant species. Now, unit of rate constant for the first order reaction. Unit of rate constant. In the previous lecture, we have seen that unit of any order reaction can be written like as mole liter inverse power 1 minus n second power minus 1, where n is the order of reaction. Since we are dealing with the first order reaction, so value of n will be equal to 1. So that will be equal to mole liter inverse power 1 minus 1 is equal to 0 second inverse, or simply we can say that the unit of rate constant for the first order reaction will be second inverse. Now, graphical presentation of first order reaction. Graphical presentation of first order reaction. So we have seen earlier that the rate of reaction R is equal to K power A. So if you compare this equation with linear line equation, y is equal to mx plus c. In this equation there is no c, so the value of c will be equal to 0. So if we plot rate against different concentration of the reacting species, we will get a straight line that will be passing from 0, that will start from 0 So the value of slope is m will be equal to k. We have another form of integrated form of the first order reaction. Kt is equal to ln A0 upon A, or we can write ln A0 upon A is equal to Kt. So if we compare this equation with the equation y is equal to mx plus c, so in this case y is equal to ln A0 upon A, slope means m is equal to k and x is equal to t, and intercept will be 0. So if we plot ln A against different time intervals t, we will get a straight line equation starting from 0 where slope will be equal to k. In a different way, this equation can be written like as Kt is equal to ln A 0 minus ln A, or we can write ln A is equal to minus Kt plus ln A0. So if we plot y against different time interval, we will get a straight line with negative slope. Where intercept will be equal to A0, ln A0. We can rearrange this equation differently. So this equation can be written like as A is equal to A0 into e power minus kt. This equation is called in exponential form of the first rate law equation for the first order reaction. So if we plot A against T, we will see that the value of A will decrease exponential with the increasing time like this. So these are the plots of first order reaction. So these are the things which I wanted to discuss with you guys on the first order reaction. We will discuss different problems based on first order reaction in the next lecture. Thanks for watching this video.